Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. We are not California dreaming, as you hear in the background by the great mamas and the papas. We are calculus dreaming still, which is the best dream of all. And today we are talking about stationary points that appear on graphs. And we have seen these, we just haven't really talked much about them and what they can tell us about the graph. A stationary point of a function is where the derivative is equal to 0. It can be a local maximum, a local minimum, or a stationary inflection, which I will refer to as a point of inflection. Now these are all called stationary points because they don't move. That's it. So this blue box is what was on the previous page. Got a lot going on here on this curve. We have a function with a domain of x equal from -5 to 6. So I'm just going to mark that. They didn't mark that here, just to make it a little clearer. So this function is only defined from -5 to +6, from here to here along the x-axis. And we're going to talk about the points A, B, C, and D. Okay, the point A is a global minimum. Now, I think that's obvious from this graph just because it is the lowest point on the graph. But the real reason it is a global minimum is at point A, the function has its lowest value at -16 1/2. So that's why we call it a global minimum. Nowhere else on the domain of the function is the value of the function less than 16 1/2. Then we move to B. It is a local maximum, as it is a turning point. Okay, what in the world does that mean? Well, if you just look at it, you can clearly see that in this local area right here, it is the highest point. But what makes it a local maximum is that the graph changes from increasing to decreasing at that point. And the slope of the curve at that point is equal to 0. And of course the slope of the curve is equal to the derivative, or the slope of the tangent to the curve. And that's equal to 0. Okay, so that's what makes it a local max. Here, point C is a local min. Same reasoning. The slope of the curve is 0 right here, and the graph changes from decreasing to increasing right at this point. It is the lowest point in this local area. It is a local minimum. And then point D is a global maximum, again because clearly it is the highest point on the domain of this function. But the reason it is the global maximum is on the domain of this function, the function has the greatest value at this point. Some functions, like the great y equals x squared, okay, so if this is y equals x squared, the global maximum or minimum is also the local minimum, and y equals -x squared, the global maximum is also the local maximum. They can be one in the same. Lowest point in this area and lowest point on the graph, least value. Greatest value of the graph and greatest value in this area. Okay, so they can be both. Stationary points of inflection. I just call them points of inflection. That's where the graph changes shape, but does not change from increasing or from decreasing. This is the great function y equals x cubed. And you can clearly see that the function is increasing, and the tangent goes to 0, and then it keeps on increasing. So remember, we have critical points when x equals 0. I'm running low on power. Can you go get me the thingy? Okay, just bring me my bag. Mrs. Becker in helping out boys and girls. Okay, and so there is no change in the function as far as increasing or decreasing, but we do get a change in shape. That is a point of inflection. Okay, so One more little slide here, sign diagram. We have a curve happening right here. And let's see, we have a local maximum here. Well, look at the sign diagram. Okay, if I just had the sign diagram, I could look at this and say, hey, the graph is increasing to the left of the 2, and then it decreases to the right of the negative 2, I should say. Well, if that occurs, I am going to have a local maximum. And then the next point where x equals 1, I have a local minimum. Now, if you notice to the left of the 1, on the sign diagram, the function is decreasing. Okay, it's going down, 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 and then to the right, it's increasing. So it's going up, 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 up. What a terrible arrow there. I'm sorry. And that's why we have a local minimum. And so then, I want to get this out of the way, we go over to this point where x equals 3. Okay? And it is a critical point because the derivative is equal to 0 there. And it doesn't change. The sign diagram doesn't change from positive to positive. Well, when that occurs, that's called a point of inflection. A point of inflection. And it could have been negative if it was negative on one side and negative on the other. That would also be a point of inflection. Okay, so that's summarized nicely in this little table here. If I'm going on my sign diagram from a positive to a negative, in other words, the function is increasing to decreasing, clearly I'm going to have a local maximum at that point. If I go from decreasing to increasing, clearly I'm going to have a local minimum at that point. Could it be global? Yes, but that has to do with checking out the function, and we'll get to that later. And if I have no change at a critical point, in other words, increasing to increasing or decreasing to decreasing, then I have a point of inflection where only the shape of the graph changes. Not whether the function is increasing or decreasing. That does not change. All right, so let's give this a whirl as far as being able to tell this without any pictures, just using calculus and algebra. So first we're going to need to take the derivative and set it equal to 0 to find where the critical points are. So the derivative is going to be 3x squared minus 6x, let's see, minus 9. And I'm going to set that equal to 0 and solve. I should have factored out the 3 right away, but I don't know. X squared minus 2x minus 3 is equal to 0. A little bit of factoring, so x minus 3 times x plus 1 equals 0. So my critical points are at x equal to 3 and x equal to negative 1. The function is defined for its entire domain, so those are my only critical points. So here we go with a sign diagram. So that's going to be, let's see, negative 1 and 3. Now, before we go any further, it says find all stationary points. So that means I need to get the x, or I need to get the coordinates of each of these before I can define them. So I replace negative 1 here, and I get negative 1 minus 3 plus 9 plus 5. So that's going to be negative 1, 10. And then for 3, I hope I can do this in my head. Oh my goodness. So that would be what? 27 minus, oh good, minus 27. So that's gone. Then another negative 27 plus 5, so that's negative 22. Phew, I hope I got that right. Okay, so let's do our test with the first derivative. For negative 2, I think I'm going to use this right here. I think that'll be easier to tell whether it's positive or negative. For negative 2, I would have a negative 5 and a negative 1, and negative times a negative is a positive. I'm going to use 0. With 0, I would have a negative times a positive, so that is a negative. and then to the, if I use 4 here, so what did I use here? I use -2, I use 0, and I use 4. I just like to keep a record of it. That's going to be positive. This is going to be positive. A positive times a positive is a positive. Okay. So at this critical point, I am changing from the function increasing to the function decreasing. So I am going to have a local maximum. Local maximum. And if I change from, well, let's see, at 3, my function is decreasing, and then it changes to increasing. Okay, so clearly decreasing to increasing is going to be a local minimum. Okay, and just to prove it to you, I mean, we've answered the question now, but just to prove it to you, you know I have it graphed. I'm going to analyze the graph. I'm going to find the maximum here, and it does indeed occur at -110, so my arithmetic was pretty good. And then let's see if the minimum, where was it that at? 3, -22. Is that what we had? Yes, we did. So you can see that here. We did it with calculus and with algebra. And I'm just showing you that it's true here by analyzing the graph. And so we can get these points without having to actually graph it. That's the whole point of doing this. I am out. Thank you very much, and we shall see you next time.